thank you all very much. I hope it's as interesting as you're suggesting. This is, I'm from the oil and gas division of Atkins. You might wonder what that has to do with renewable energy. Wave energy is the machines that get the energy out of the waves. And the answer is that they're the same technology as offshore oil and gas. Those hurricanes that we heard about from earlier speakers, I don't think anybody is more interested in the nature of the waves that they produce, which are like this, breaking waves, than the oil and gas industry, because they go right across, in the US Gulf, they go right across the oil rigs. And the computer programs that we use to analyze the oil rigs in the States are just the same as the ones we apply to wave energy machines here in the UK. So, this machine, Polaris, is the state of the art in wave energy converters that take wave energy and produce electricity. And we've been working on it at Atkins for 10 years now, doing the design verification, independent verification of the design. Now this machine works by, it's steel tubes here, 4 meters diameter and about 30 long, with solid ballast to bring them down to floating at about mid-level. And they're interconnected, so there's 5 of them, interconnected with a universal joint, like on a truck transmission shaft. And around the universal joint are 4 big hydraulic rams, and when the device follows the profile of a wave, as you see it doing here, the bending moment, the bending effect in the device is translated into pressure in the hydraulic rams, and oil is pumped first to accumulators, which smooth power flow, and then to a hydraulic motor, which drives the generator. And 2 of these machines have been installed in Orkney for a year or 2 now and generate a significant amount of power. And this is a considerable technical achievement. Many people have failed to produce working wave power devices. This is a working wave power machine. Now, part of its motivation is commercial. This is private sector work almost entirely. Very little government support. Proportionately. Part of the motivation was that we owe it to our grandchildren to look into this possibility. Richard Yem, the founder of Polaris Wave Power, once said to me that if he ended up ruined and in the gutter drinking cider with the other down and outs, he would be able to say, "At least I tried. At least I tried." Indeed, Richard, did a bit more than try. Yes, wonderful. Now, the cost of wave power is currently much greater than offshore wind, but of course these are early days. A good question is, what are the ultimate cost limits for this technology? And I thought this was appropriate for this forum because mathematicians have already helped very much with this question. Isaac Newton himself was a well-known interest in waves, and several of his successors here in Cambridge were very interested in water waves, and I will mention that as we go along. So, this is the contribution of the mathematicians to wave energy, which is to say something no engineer would say, which is never mind what's happening close to the machine, which looks like it's the most important thing. Consider what's happening a long way away. Let's see if this, there we go. A long way away from the machine. Let's go back one. We're going to consider like a kilometer away, and we're going to consider the what the waves are doing there. Here we are. Now what we've got is the incident waves that were there anyway before. Here's the Polaris machine, before the machine was there. They just go through like that. And then the extra waves produced by the presence of the wave power machine are all radiating outwards, just like if you drop a stone in a pond, the waves radiate outwards in a circle. So we can consider the power flux through this circular control surface, and we reach this conclusion that the incident waves produce zero net flux because what goes in one side of the circular control surface goes out the other. The radiating waves, well, they're just an energy loss. They're taking energy out of the system. See, what we wish to do is to equate the energy, net energy coming in through this far field to the power produced by the device. But there is a third term here. Because energy flux is pressure times velocity, there is a cross term between incident and radiating waves, which is a very complicated term of flux in and out alternately all the way around. But there is a classical method invented by George Stokes, who was one of Newton's successors here in Cambridge. And also well known, by the way, in the oil and gas business. All oil rigs, just about, are designed for Stokes' fifth order wave. That's Stokes 1847. The very same formulae derived by Stokes are used every day in the oil and gas business. Anyway, his method, another thing he did, his method of stationary phase allows you to integrate that lot up very neatly, and the power, net power input is just depends on the waves radiating in the down wave direction only. So what we want to do from a theoretical point of view is to have the maximum waves radiating down wave and minimum in all other directions, because they were just producing the loss, as I was describing earlier. Now the loss is proportional to the amplitude squared, and the input term from Stokes' method of stationary phase is directly proportional to radiated amplitude, so we can easily do the optimization, and we conclude that there's a maximum theoretical power which depends just on the angular distribution of the radiating waves. And if it's a monopole far field, so that would be produced, say, by a heaving buoy type wave energy converter, the capture width comes to the wavelength over 2 pi. And if it's a dipole type far field, which would be produced, say, by a seabed mounted flap, then the capture width, which is, by the way, this is the, I should define it, it's the width of wavefront with the same power that the device is producing. And its maximum is twice that for a dipole type device. And this result appears to have been derived simultaneously by several mathematicians, not least in the UK, David Evans at Bristol University. And this insight leads to the conclusion that Polaris will have a very nice high maximum capture width because, it's these tubes, the most important motion for radiating waves is vertical, and their motion is delayed by the wave speed down the device. So down wave in this direction where we want to maximize the radiation, the contribution for the 5 of them adds up constructively. In all other directions it interferes destructively. So it's, from this point of view, Polaris looks very good. Where are we now? Okay. Now here's another result produced by the mathematicians. This time this is Nick Newman in the States in 1976. Very interesting result. That can you relate the power output to what the machine would do in still water if it will run backwards? So all its hydraulic rams receive power and the thing runs backwards, as it were. It turns out you also have to run time backwards to make the theorem work. You have to, so in the case of Palamis, you would have to, by running time backwards, I mean, make it look like it would look if you made a cine film and played it backwards. Okay, so in the case of Palamis, the wave-like motions propagating along it would propagate the other way, from tail to nose. If you do all that, then the theorem is that the power outputs related to the waves radiated in an upwave direction, the other way. And that is a very useful and simple result. I mean, we've had people walk through the door in Atkins with a wave power machine, which they wish us to give an opinion on. And it's very easy to give an opinion. Consider it in still water. You can show with a back of envelope calculation that it will not radiate hardly any way. It has very poor wave radiation. So independent of any engineering consideration, it must be a bad wave power machine. So that is a very positive contribution by the mathematicians here. Now here's another theoretical insight. For both the monopole and the dipole radiator, the wave radiation is proportional to the force the machine applies to the water. So we conclude that the power input term from Stokes' method of stationary phase is the product of this force and the particle velocity of the instant wave. And this is just like a wind turbine, where the power is the force on the turbine times the wind velocity through it. So we immediately see that the average wave particle velocities over a year, root mean squared say, are much lower than wind speeds. So the forces and thus the cost must be much higher. And that's basically why wave power is so difficult. The density of the fluid is immaterial. What counts is the velocity. And because wave particle velocities are much lower than wind speeds, wave power is inherently more difficult than wind power. Come again? Sorry.
I was just muttering.
Oh no, mutterings do interrupt.
It would be lower power because of lower speed for the same force.
That's right. Or alternatively, for the same power, you need a lot more force, and other things being equal, force is cost, roughly speaking, in engineering.
Then the question would be, would you get more force out of water than you would out of air?
Well, you could easily, but only at, roughly in engineering, you could do it, but easily perhaps, but expensively. So, now here's another theoretical insight. This one due to Richard Yem, whose background was wind turbines, by the way, before he got into wave power. A wind turbine feathers its blades as the wind rises. It to limit the force on it, it feathers the blades. It takes less power out of the wind. And that's a very important advantage of a wind turbine because it makes the most of its force carrying capability. It doesn't, in a very strong gale, it doesn't try and get the maximum amount of power. It just gets as much power as the structure can stand. Now that's a very good plan. I mean, that is what the accountants call sweating the assets. You've got an asset, which is something that is your strength, and you're doing it, and you're using it all the time, or as much of the time as you can. Okay, so when Richard Yem arranged this on the Palamis machine hydraulically, the hydraulic machinery is very good at naturally limiting forces. You just have a pressure relief valve, and that limits the force on his rams. Okay. Now here's an engineering consideration. This is a problem of maintenance, which is a big deal with offshore wind turbines, by the way, and wave power machines. you must have the maintenance cost well below the revenue, obviously, for the thing to make economic sense. And a good question is, what is the maintenance cost of these things ultimately going to become? A sanguine example is that it will go down and down. Here is a famous example. This, isn't that beautiful? This is the Harrison chronometer, the first watch accurate enough for determination of longitude. It took him 30 years to develop it. This sort of size. Just leave the engineers alone, and over 200 years, that thing comes down to this sort of size, even more accurate, even more reliable, zero maintenance. So that would be a cheerful view of what will happen to maintenance costs. A less cheerful view would be this. This is the hovercraft car ferry, which was on the Channel, as people my age will remember, some time ago, but was replaced in 1990 by Australian-built aluminium high-speed catamarans, which are still on the service. And the reason was maintenance. This thing, look at the rubber skirt here. This bit's all right. That lasts for years. But the bit that touches the water gets a hammering from the waves and is a severe maintenance problem, to say nothing of all this lot. This is like a helicopter. High-speed gearboxes, gas turbines, drivetrains. The whole thing was totally uncompetitive from the maintenance point of view compared with Australian catamarans. So that, I don't know, if I knew for sure how these questions would turn out, I would say I don't. I'm just saying it's a difficult engineering question. Here is my suggestion as to we might make a very maintainable and survivable wave power machine. This is to use a dracone. Now dracone is a fluid-filled rubber tube. These ones are half-filled with fluid and they're water and designed to act as a protective boom for this warship. The more standard use is to fill them completely with, say, diesel fuel and then tow them with a tug. And the military like them because they're air transportable, which a oil tanker certainly isn't. And then they're highly maintainable. If you make a hole in it, you just, it's like a bicycle in a tube, you put a patch on it. So, now the property of a rubber tube full of water that makes it interesting for a wave power machine is that it will propagate bulge waves. And here is a rubber tube full of water, and you see it can propagate a bulge. Isn't that nice? Now this is all standard physics. The best known example is medical, actually. Our pulse from the heart goes around our arteries as a bulge wave. And this was a favourite topic of James Lighthill, who was very interested in wave power too, and was another of Newton's successors here in Cambridge. And in his marvellous book, Waves and Fluids, he gives a theory of all kinds of things, not least bulge waves, and he shows that the theory is just the same as the theory of a sound wave, but you've effectively reduced the compressibility of the water through the sort of distensibility, the stretchiness of the tube, and that's what slows the wave down. So for a wave power machine, the plan would be to put this thing in the water, floating just below the surface, a couple of meters more diameter and hundreds of meters long, and then we will get a bulge wave excited by the water wave, and it'll have the same length and speed as the water wave. But if the speed is the same as the natural speed of the bulge wave, which I just showed you, then the wave can anyway go at that speed in the rubber tube. So in that case, the amplitude of the bulge wave is theoretically infinite on a simple theory. And it's exactly analogous to a pendulum. If you excite a pendulum at its natural frequency, the response is theoretically infinite. So, now I've been working on this with Francis Farley for some years now, and he and I believe a good plan is to take the power out of the bulge wave all the way along the device with a distributed power takeoff. And this is the simplest, but maybe not the cheapest way of doing it, which would be to squeeze the rubber tube like this with pneumatic rams. And this time the rubber is inelastic, like a sidewall of a car tire. And you put the fibers round circumferentially, so it's very strong in a circumferential direction, but no fibers the other way, so it's weak longitudinally. And the longitudinal force is carried by this linkage here, which these little rods interconnect the rams with these spherical bearings, the standard thing on the end of a hydraulic ram. So it's flexible as a chain, and it carries all the longitudinal pressure load. Now the distensibility that you require to propagate a bulge wave is provided by the compressibility of the air trapped above the piston in the pneumatic ram, and that will fluctuate as the bulge wave propagates, and that's easy to take the power out. You take the power out with, just like on Polaris, with a valve which releases the air, in this case when the pressure is high, and then another valve which lets in lower pressure air when it's low, and you collect all the high pressure air and all the low pressure air, and then a turbine between the two is where you eventually get your electricity. So now that is perhaps subject to the criticism that it's into all this mechanical engineering, these spherical bearings. So it's possible to conceive of a more ambitious design with no mechanical engineering. This one, see, the advantage of a distributed power takeoff is that you can make the device as long as you wish, maybe 5 times the length of Polaris and about the same immersed cross-sectional area. And that's good mass production. You know, just work a night shift and make it longer. It's good economics. Now here's a more ambitious design. Now this time we've trapped air in the top half of the bulging tube. The tube itself doesn't bulge, its outer wall is inelastic like the last one, but these are air chambers above this red membrane, and the air there, its compressibility gives you the distensibility of the water column that you require to propagate a bulge wave, and the air, which is now just at a 1 or 2 bar low pressure relatively, then its pressure fluctuates as I described before, and then these are the one-way valves, and then the low and high pressure ducts, just like I showed before, but the whole thing running at much lower pressure. So, and that has no moving parts at all apart from these one-way valves. So these are my conclusions. So having worked on Polaris for 10 years now, through the prototypes and various early production versions, I believe it's close to an optimum wave power machine. I think it is. It's I can't can't think of any way to improve on it. Short of, this is if you're using conventional technology, which was Richard Yem's aim, to use standard components, standard hydraulic rams, standard steel fabrications and castings. But perhaps if you do something very radical, like switch to completely unconventional technology, distensible tube, then you end up with something which is hydrodynamically equivalent. I mean, it's just the same. It's a line of monopoles perpendicular to the wave crest, just like Polaris, but it's even longer, maybe 5 times as long. So it's even bigger capture width. And that is the kind of way that looking ahead, as I believe it's our duty to do to our grandchildren, because they're certainly going to be annoyed with us for burning up all the oil and gas. And it's our duty to, surely it is, to look into all this stuff now. So this is why I think we should keep doing it. That's all I have to say. Thank you very much.
So for our final speaker for this session,
Oh,
we have
glad you
our
liked
panel
it.
session.